Okay, I don't have much left in terms of notes. We'll see how far I get with that. I guess there's a possibility. Well, actually, no, I probably wouldn't finish it all today, but maybe just over the course of 2 days. Okay. On Thursday, class will be fully virtual because once again, I'll be going down to the coast one more time to teach 460/560. That's the last time I'll do that this semester. So, okay. You should start thinking pretty soon about what you would prefer for the timing of the oral final. I should give us more information on that. I'll try to do that on Thursday, as far as what areas to focus on. I mean, it's all about the notes. I'm going to look at the notes to figure out what I'd like to ask. So,
Okay. Just like a comprehensive list of all the questions you'll ask us.
Nice try. And then in some cases, I might point out like, oh, I will definitely ask something about this, but yeah. Consistency, stability, convergence. That's a given. So there, that's something. We'll breadcrumb for you. Okay. And as a reminder, Friday, December 10th is when it's all got to be in, as far as the homework is concerned.
So have everything done the 11th.
You say the 11th?
Yeah.
Since that whole weekend is going to be ruined by grading anyway, because it's not even this class that's the problem. It's going to be 460 for sure, because there's more students there and quite a few slackers. So it is possible to take in some things that come in over the weekend. Although my goal is the grades are due Monday morning, so I'd want to like go into SOAR and put the final things in like Sunday evening. But I'm saying the 10th to all my classes because if everybody took as much leeway as possible, then
you'd be grading at like 3 o'clock in the morning on Sunday.
Yeah, and I would be grading angrily, and you really don't want that. So, okay, so it's for your benefit that I'm saying the 10th. So, okay.
My favorite, sorry, I'm gonna have to digress real quick, but my favorite was Walker got his student emailed her from a semester prior being like, is there any way I could do extra credit to boost my grade out? So this would be like a spring student emailing you now. Can I do extra credit to increase my grade?
A student she had in the spring.
Yeah.
Emailed her now.
Yeah. Not quite that timeline, but basically that setup. Basically
okay.
a past semester
like so a whole semester later.
Yes.
Okay.
That's my favorite story of one of her students.
Well, I actually am aware of that taken to a greater extreme in two directions.
Oh no.
This was from one of the teaching groups on Facebook, where Society for Stressed Professors, and there are many of us, and where a professor got an email from a former student who was, so the former student was asking this professor to change the grade for a class taken several years ago, a student long since graduated, and it was not even that professor's class because the professor who actually taught it was no longer at the university, probably retired. And the reason was that they wanted to get into nursing school and needed a particular grade in like anatomy and physiology, and so asked for that grade changed. So yeah, apparently, I mean, okay, I know that I'm not the deadline type, but
It's a little too far ago.
yeah, even I say there's a limit. So, yeah.
I just find it really funny when the students ask us grad students of favors like that, and I'm just like, do you know how low I am on the totem pole? I do not have that kind of power that you think I have.
I think that I have a feeling that students, undergrads, especially like freshmen, don't really know the totem pole. I guess that in their minds there might not be too much of a difference between like y'all and me or something because you're a teacher.
I know. I tell my students, I'm like, I'm a student too, because I told them straight up. I was like, all right, y'all, let's be real here. If we have our test after Thanksgiving break, who's really going to study for it? Because I know I am not doing my homework on Thanksgiving break.
Yeah. Well, one of my colleagues was talking about how a student came to him looking for his like 101 instructor who was a grad student, and this student referred to the GTA as doctor and the professor as Mr. So yeah, so the lines are blurred in their mind. So yeah, and how many of your students call you doctor or professor?
Yeah, it's happened.
Yeah.
I don't even have a lot of students.
Yeah.
Yeah. My first semester here, I started on curriculum like the first half of the semester, but then enough kept doing it. I'm just like, forget about it.
Oh yeah, because at least they're elevating you.
Yeah.
Right?
Yeah. Whereas when I would teach like 102, so glad I don't teach that anymore. Even after saying something at the beginning of the semester, I still have students calling me, oh my goodness, Mr. Lambert.
Oh.
Which is funny because we actually had a grad student several years ago. His name was Jamie Lambert, and so that was caused some confusion. Yeah, and the thing is, I'd want to correct them. I was like, oh God, I'm going to look like some sort of academic snob or something. But yeah, it's but sometimes would anyway because I get tired of that. It's like, oh yeah, make me feel old and PhD-less.
I just tell them I'm grateful. I just am grateful if they get any kind of pronunciation close to my last name, because somehow people have changed my last name into being like, your last name is Panther, right? And I'm just like, there is not an N anywhere in my last name. How did you get Panther?
The Math Panther.
I should sign that on all of my official USM emails
Yeah.
now.
Yeah, we need like a graphic and everything. There you go, the Math Panther. Oh yeah. Well, I've been called Landers because yeah, obviously I have an N in my name too. So
Well, mine is Prather.
yeah.
Where do you find an N in that at all?
You'll never guess what mine is. Shrimp. It's like the same concept, like they look at our names and they just want to say the word that they know.
So I've
But that I could understand a little bit more than Prather into Panther.
had
Yeah,
people
they
who
were
pronounce my
really
name as
bad.
Holy. I've had people who pronounce it as Pussy.
I guess we're just living in a literate society now.
I told Robert he should officially go by Mr. Hussey from now on. Sarah was talking about a weird noise. Oh yeah, Sarah was talking about a weird noise and she walked out of this room, but I didn't think anything of it.
Out there, but yeah, that's kind of wrong. But the thing is, I didn't actually know until this moment that your name is pronounced Prager. I thought it was Prather.
Everyone thinks it's Prather.
Okay, yeah.
So that's why I respond to Prather, but it's Prather.
Yeah.
I just know.
Okay, good enough.
Yeah, same. I always thought it was proper. I said it, but I didn't know.
All right, well,
It's bad enough that I will respond to Prather and I don't bother correcting people because I'm like, it's close enough. It's fine.
oh yeah, yeah. All right, well, now we've all learned something today.
I at least see how you got the pronunciation of Prather because it's just changing the way you pronounce the A.
Yeah, yeah. At least I didn't insert new letters or
Yes.
or delete letters.
Which you have to do both. You change it into Panther.
Yeah.
My boss's name was Kimbia, and I always thought it was Kimbaya. That's what I always called her when I talked to other people. So finally, I called her Kimbaya, and she was like, "No, it's Kimbia." So it was the same thing. It was just like it's Kimbaya. So I don't know. I thought it was Kimbaya.
Yeah, it's too subject. Okay, kumbaya. Yeah. I don't know. I think a lot of people have names that I think their parents just wanted their child's name to be mispronounced or misspelled all their life. But you know, all in the name of uniqueness or something.
At least you don't have the name of Elon Musk's kid.
Yeah.
Oh, I forget what that is.
It's just a random grouping of letters.
Oh, yeah,
And numbers.
yeah.
Like
Well,
XE2 something, I don't know.
okay, well, he can pay for therapy. Okay. Multi-step methods. So, you've seen one kind of time-stepping method so far, it's the Runge-Kutta method, so here's a whole other class of them. Okay, so to contrast, one-step methods, which includes anything in the Runge-Kutta family, they use information only from this interval in time, Tn to Tn plus 1. To compute the solution at time n plus 1. That's what makes it a one-step method. It's only working with that one step in time. Whereas multi-step that goes back further in time. So using older information. It might seem kind of strange, but actually it's quite beneficial. So what I'll do is write out a general S-step method. So S is the number of steps in the method. So S equals 1 would just be back in the one-step category. So all multi-step methods have this form. So on the left side, you have coefficients, alphas, multiplying y values.
God bless you.
Dang it.
God bless you.
Okay. Equal to, oh, whoops. I actually didn't notice I have superscripts, but on the board I've been using subscripts, so I'm just going to stick with that. Okay. Delta T. And then you have this like combination of F values. Oh, this should be N plus J. Fn plus J. So this is for the standard first order ODE, y prime equals f of t y. And this notation, Fn is just the function f evaluated at Tn Yn. So it's a convenient shorthand. Alrighty.
I'm just convinced the building's haunted.
Well, I had a problem a few years ago where in my outer room, birds were getting in there.
What?
Yeah, but they would go enter the building, like the attic, I guess, and somehow they'd be able to get down through these ceiling tiles into my outer room. And so one time when I go into my office, there's a dang bird flying around in there. But then one time when I came in on a Monday morning, there was a dead bird that was trapped in there all weekend. So I made sure that they found a way to prevent entry. Because, you know. But yeah, I'd hear a bird flapping its wings, and then one time it flew into my office, and like, well, at least somebody's showing up for office hours. But, now, one thing I want to point out is the distinction between multi-step methods and rung-and-cutter methods. What we saw last time, the rung-and-cutter methods, is F was evaluated at all different kinds of points, like Tn plus something, Yn plus something, and many different combinations were possible, especially in a method like fourth order rung-and-cutter. You're having K1, K2, K3, etc. But not in multi-step. Multi-step methods, anytime you evaluate F, it's always at some Tn, Yn pair. And that simplifies things quite a bit. So what ends up happening is, we only have one new evaluation of F per time step. Okay. So that's very important because a key advantage of multi-step methods over rung-and-cutter methods is they are more efficient. So there's less work per time step because you're relying on values of F or values of Y that were already computed. There's very little new that's coming out of each new time step. Okay, so to give you perspective, contrast with fourth order rung-and-cutter. Each time step calls for 4 new evaluations of F. Alrighty. Now, you have these betas here. Beta 0 is 0. That means that the method is explicit. Otherwise, implicit. Actually, I need to check. Oh, not beta 0, beta S. One thing that's kind of frustrating about multi-step methods is how they are described. If you go to different books, they're talking about the same multi-step methods. It can be written in different ways. This is not the way that I normally write about them. So I got a little thrown off there, but I'm sticking with what I got from the notes that I inherited. So that's why I'd be more careful about that. Because if you look at the highest index that we have in this whole method is n plus s. So that is the newest y value that you're computing. So if suppose beta s was non-zero, then we would have yn plus s on this side of the equation and here because of this. So that makes it an implicit method because that's the new value of the solution you're trying to compute, and you must solve that. You must solve this equation using some sort of iteration like Newton's method. But if beta s is 0, then there's no such term on this side. Yn plus s appears only over here. So then you can rearrange this equation to isolate it and compute it that way. Okay. All right. So what I'll do now is give you some examples of multi-step methods and also describe certain categories of multi-step methods. Okay. So first category of multi-step methods shows Adams batch for methods. Okay. Now these are all explicit. Okay. And they all have something in common, that alpha n plus s, so the most recent alpha is always 1. The one right before it is always equal to -1. And then all other typos in these notes here, I need to fix these. All other alphas are 0. J equals 0 up to, oh, wait a minute. Something is really wrong here. Okay, sorry. These notes suck. Not sure how much of this I got from MIT and how much was my own writing. I don't remember. I was adapting some notes. But regardless, they need to be fixed. Okay. Okay, this is correct. So for the most recent y value, the one you're trying to compute that time step, coefficient is 1. The one before it, coefficient is -1. There are no other terms on the left side. So mainly it's the betas, those coefficients that determine the specific Adams-Bashforth method. Okay. Now, so the idea is you figure out how many steps you want, what the value of s is, and that's going to determine all the coefficients. So for s equal to 1, so that's a one-step method, you get yn plus 1 is equal to yn plus delta t fn. So what I've done in this case, this term, based on the form I wrote earlier, would be on the left side, but with a coefficient of -1. So I've just moved it over to this side, so it has a coefficient of 1. But this method, you've actually already seen. Can you tell me what it is? Close. Forward Euler. None of you are going to volunteer, Pat?
Well, what I thought was, we're using n, right? That's what I was doing.
If this was n plus 1, that would be backward. Yeah, to match the y value shown here. Okay, yeah. Okay. Yeah. But But people, take a chance in the answer. Put something out there.
I'm good.
I know, you're all afraid of being wrong. I was actually telling another one of my students, like one who's not in this class, I literally said these words, embrace the wrongness. Because
I'm good. I did that already, and it was a very traumatic experience. I'm trying to forget it.
okay.
It was not a good day. I was very upset.
Oh, I'm sorry.
It's okay.
But the point is, you're still at it. So.
I question that decision every day sometimes.
Okay.
And then Robert threatened to beat me up and drag me back to the program if I try to leave, so I'm here.
Okay.
I didn't say beat you up. I just said I'd drag you back here.
Okay, but still, there were 4 other people in this class who could have suggested that if it was not backward Euler, that maybe it was forward.
We all do it. Like,
Yeah.
I didn't even know what he said first time.
He said backwards Euler.
Oh, okay. All right, you're excused. But you, Chandler. Okay. All right. Now, okay, so that's so Euler is both a multi-step method and a Rooker-Cutter method all at the same time. But not a very interesting multi-step method. So a true multi-step method is yn plus 2 is equal to yn plus 1 plus delta t, and it's a linear combination of 2 f values, n plus 1 minus 1/2 fn. Okay. Okay. One thing that's worth pointing out about these coefficients, the 3/2 and minus 1/2, they sum to 1. And that's going to be true in general. But for a method to be consistent, these coefficients need to sum to 1. Okay. And then for different kinds of events will lead to different coefficients. You can actually look up in Wikipedia like Adams methods, and this would come up. I can actually give you a formula for these coefficients. So the formula for beta j is actually okay. What else? The integral from Tn plus s minus 1 up to Tn plus s. So the current time is the upper limit, the previous time is the lower limit of the integral. And the integrand is a Lagrange polynomial of degree, make sure I get this right, s minus 1, index j of t dt, for j equals 0 up to s minus 1. Okay. So we have the integrals of Lagrange polynomials. And where that formula comes from is from the following. If I have y prime is f of t y, I can integrate both sides of this with respect to t, and I get the following. Y at time tn plus s equal to y of tn plus s minus 1 plus the integral okay. So that is exact. The exact solution satisfies this equation. So then what you can do is to approximate this, because the problem is you can't compute this exactly because you have y of t, your unknown, in the integral. So what you do is you approximate this integral using a quadrature rule where you're integrating from here to here, but this is from quadrature with a choice of nodes being Tn, Tn plus 1, up to Tn plus S minus 1. Okay. All right. Now, you may remember from when you first learned about numerical integration, I believe everyone here has either taken 460 or 560 or my topics class from last fall. I think Chelsea's where you would have seen this. This is interpolatory quadrature, where you approximate the integrand by a polynomial and you integrate the polynomial exactly. In such a quadrature rule, here are the nodes that are chosen. The weights are the integrals of Lagrange polynomials. That's what leads to this formula right here. But 1 over delta t factors, because if you work this out, because the interval is of size delta t, there's going to be a factor of delta t in here, but we want to write the method to have a factor of delta t out here, separate from the coefficients. So that's why there's a 1 over delta t factor here. Okay. So therefore, it's not too hard to figure out what these methods would be for a given value of s. S equals 3, 4, etc. All right. The order of accuracy of these methods, order delta t to the s, which makes sense because with s equals 1, that makes it first order accurate, which we already knew that forward Euler is first order accurate, so it just goes up from there. All right. Questions on any of this? Okay. Just for a historical note, the name makes it sound like these methods were a collaboration between somebody named Adams and somebody named Bashforth, but they're actually simply developed by Adams, John Couch Adams, in the late 1800s. So when I say in some of my funding proposals that time-stepping methods need to be updated because we're using time-stepping methods invented literally over 100 years ago, I'm not exaggerating.
We have faith that you could find an updated method, Dr. Embers.
Okay, so that's already done. Check. Bashforth came up with the differential equation that these methods were designed to solve. So Bashforth provided the problem, Adams applied his numerical method. Okay. All right. Well. I will mention that one of my students, Bailey, has been working on a multi-step version of my Credo subspace spectral methods that has an appearance similar to what you see here. It's just that this is applied for each Fourier coefficient of a solution individually, where the coefficients of the betas here are different for each frequency. And the formula for betas is actually this, except for additional factor, a weight function that's included in the integral that leads to that frequency dependence, and it has all the same benefits of multi-step methods. Only one new evaluation of your time derivative per time step. Same order of accuracy, but certain other properties that I'll get into later when I talk about stability that are more favorable. I have suggested that these methods be named after her, like Adams Bashforth-Rester methods, but I'm not sure if she'll go for that. I know I would never want a method of mine to be named after myself. I mean, it just feels too weird. Okay. Now, all right, so that's one class of multi-step methods, and then there's another that is extremely similar. That they are also Adams methods. They're called Adams-Moulton methods. Okay, and these are implicit. The alphas have the same property. The betas have the same formula as before. It's just that now the Lagrange polynomials have a degree 1 higher. We're using one more interpolation point. So the nodes go from Tn up to Tn plus S. Okay, all that's the same. Because there's one extra interpolation point, the order of accuracy is delta T to the S plus 1. When S equals 1, we have now backward Euler. And then a two-step Adams-Moulton method is, okay, so y plus 1. Okay, yn plus 1 equals yn plus, okay. Oh, wait a minute. Oh, something's not right here. Oh. Hold on, don't write anything for her. Not yet anyway. Okay, that's n and n plus 1, n and n plus 1. Interesting. Okay. N plus 2, n plus 1, and n. Okay, so both of these are actually really they're one-step methods. But the thing is, okay, this is bothering me because there's no way that because this is first order accurate, this is second order accurate. Okay. I'll erase this because this is no different than before. Okay. I'll write down the two-step method. Okay, so what we have here is 5/12, 8/12, and minus 1/12. Right. Okay. Okay. Now, so first method, backward Euler, first order accurate. Second method, is second order accurate, and we've actually seen this method before. It actually is also a Runge-Kutta method. Anyone tell me which method this is?
Big points.
No. The midpoint rule would use like information at time t n plus a half. It is a trapezoidal method, yeah, because it uses n and n plus 1, and here we have a trapezoid area formula here. Now, the key here is these are all Adams methods that come from this formula. It's just that this one uses 3 interpolation points. This one uses 2, and this uses only 1. So really, this first one doesn't exactly fit this because it uses 1 less index. But these other 2 do come from that exactly as written with the appropriate value of S. Notice once again, the coefficients, the betas, sum to 1. Again, required for consistency. All right. Adams Multistep methods were also invented solely by Adams. The reason Moulton's names come to mix because later Moulton recognized that Adams' 2 families of methods, the explicit and implicit, can be used in combination, and that's called a predictor-corrector method. So if you combine some chosen Adams Bashforth method in combination with an Adams-Moulton method, you get, okay, so predictor-corrector. Now, what does that mean? Because if you use an implicit method like this by itself, you have to perform an iteration. So you need some, like here, you're trying to compute yn plus 2 from yn plus 1 and yn. You need an initial guess, and then you could do something like fixed point iteration or secant method or Newton's method to solve this equation for yn plus 2, because yn plus 2 is going to appear in here. Now, as an alternative, if you do have a predictor-corrector approach, what you do is use the explicit method first, and that gives you kind of like an initial guess. That gives you a good approximation of yn plus 1 to start with. Then you take the yn plus s from here and substitute it on the right side of this method. So now, even though this is an implicit method, you're no longer really using it as 1, because you have a value to substitute on the right side, and then you use that to compute this output value here. Now, if you wanted to, you could iterate from there, just treating a value from the predictor as a really good initial guess. But you don't have to, really. Because since this is already a value of y at the correct time, it is a really good initial guess. So do you really need many iterations anyway? Not really. So you can just use this method once. And so that's that's more efficient than using an implicit method by itself and carrying out the iteration. And it's been proven that what the order of accuracy is for this, it depends on both methods. So you might choose to use a higher order explicit method in conjunction with a slightly lower order implicit method, and get this order of accuracy. So you have choice there. Like there's there's no expectation on what the order of accuracy is of one method versus the other. You can combine any two methods, but keep in mind the lower order of accuracy is the one that will prevail. So you should keep that in mind when choosing which method to use as a predictor and corrector. All right, so questions about implicit methods. Okay. All right, I have one more category of multi-step. Okay, so we also have backward differentiation formulas. Also known as BDF. And these are implicit, all of them. And whereas with Adam's method, you had certain predefined values for the alphas, here we have predefined values for the betas. And you have beta n plus s is equal to 1, and all other betas, beta s is equal to 1. All other betas are equal to 0. So they have one term on the right-hand side. So as an example, for a case of s is equal to 2. So we have 3/2 yn plus 2 minus 2 yn plus 1 plus 1/2 yn is equal to delta t f n plus 2. Okay. So the idea here is the way you get these coefficients. First of all, the coefficients will always sum to 0 in this case. These coefficients come from a numerical differentiation scheme. So what you're doing is, on the left side, you're supposed to approximate y prime at time n plus s. So that's what's being done here. So if you're trying to get a derivative at this point, and you're using these 2 points to help yourself get it, those are the coefficients of your numerical differentiation scheme. And y prime is equal to f, so that's why you have just f on the right side. Man, so many typos I'm finding in the notes. Backward Euler you could think of as a backward differentiation formula for a case of s equals 1. The accuracy of a BDF is delta t to the s, just like Adam's batch form. But I should mention that you might think, oh, okay, so I can choose a high value for s to get high order accuracy. And yes, you can to a point. Unfortunately, these methods are known to be unstable for s greater than 6. It's it's worth mentioning that one of the most powerful ODE solvers in MATLAB, ODE 15S, S is for stiff, uses BDFs. So the 1.5 indicates variable order, so it uses BDFs of order first through fifth to solve whatever ODE you give it. And this is for stiff problems like those that come from PDEs, it worked quite well. Which is unfortunate for me because when I'm implementing a new method to try to get it published, I have to compete against that, and sometimes that can be quite difficult. It puts up a good fight, anyway. Okay. Now, let's see. There's one thing about multi-step. Okay. First of all, not all multi-step methods fall into these categories. So there are multi-step methods that are neither Adams methods nor backward differentiation formulas. So here's an example of an unclassified multi-step method that doesn't fit any of these baskets. It's called Simpson's method, named for Simpson's rule for numerical integration. I actually wrote rule, but it just doesn't need to be called Simpson's method. Yn plus 2 is equal to yn plus, okay, I want to make sure I get this right. Delta t over 3 at n plus 4 fn plus 1 plus fn plus 2. Now, I actually have this method mentioned in my book, and I was writing it just now from memory. So now I'm going to check and make sure I wrote it correctly. Okay. Let's see, multi-step methods. Where is it? Ah, found it. Wow, I got it right. I'm honestly a little shocked. Okay, now, so this method, it's a two-step method, which you can see because it uses information at time n plus 1, and n plus 2. But it's fourth order accurate, which is quite unusual. For a two-step method, because like for an Adams method, best you can hope for if a two-step method is maybe getting third order accurate. But it's fourth order accurate because of a fourth order accuracy of Simpson's rule. You may recognize the weights from Simpson's rule, where the point in the middle gets 4 times the weight of the values at the boundaries. So that's where the method gets its name. But it's not really a great method. Whereas Adams methods are, and I'll have to get into this later, strongly stable, Simpson's method is only weakly stable. So, so that's one unfortunate thing about it. But just to let you know that not all methods are Adams or BDF. Okay. Another hugely significant point about multi-step methods in general, it's a significant drawback that all multi-step methods require starting values. Okay, so what do I mean by that? So let's take a look at, okay, as a simpler example, this method right here. So when you go to solve an ODE, what are you given? You're given y0, the initial data. So from there, you need to get y1, y2, y3, etc. So if I set n equals 0 in here, I have y2 is equal to y0 plus, and here I have f0, f1, and f2. I don't have y1. And therefore I don't have f1 either. So you cannot use a multi-step method fresh out of the gate. You have to generate enough values to be able to apply it. So for example, if you have a, let's say a 5-step method, then you need, you need to take 4 steps. So for example, so simplest case, 1-step method, you don't have to do anything because you have all the values you need already. A 2-step method, you need to take 1 step using something else. So 1-step methods are still needed. You have to use some 1-step method to generate enough starting values so that you can apply the multi-step method. Now, you're only doing that for a few time steps, so you still gain the efficiency benefit of a multi-step method because most of your time steps will be with a multi-step method, but you have to do this up front. Okay. Also, technically you can use whatever 1-step method you like, except you really should make sure it has at least the same mode of accuracy, if not better. So as an example, suppose you want to use a, let's just say a 3-step Adams-Moulton method, has 4-fold order accuracy. Then you should consider using 4-fold Runge-Kutta to generate your starting values. If you use, say, trapezoidal rule instead, that is only 2nd order accurate, your entire solution will be tainted. It'll be 2nd order accurate from that point on, because you have that 2nd order error that is basically infecting your solution, and it will contaminate the rest of your values. So, so make sure that the order of accuracy of your starting values method and your multi-step method are consistent. Okay. But a lot of software for solving ODEs makes use of either Runge-Kutta or multi-step methods, because multi-step methods, you have that efficiency advantage. Okay. All right. We don't have a whole lot of time. So, well, this is all I have for multi-step methods anyway. The only topic I have left to cover is about stability analysis, which amounts to, 2.5 pages of notes. So I figure I would cover a portion of that on Thursday, and then I have von Neumann stability analysis, which is the last topic, and I probably do that like on Tuesday, the following Tuesday or whatever. Yes, we are having class the Tuesday before Thanksgiving. Deal with it. You can watch the video if you really need to. Okay. Yes, it's a whole. If I'm going to suffer, you're going to suffer kind of thing.
And if it makes you feel better, I already told my dad, like, hey, Dad, we're going to leave like first thing Tuesday morning because I need to be at your place before my class starts.
Yeah. Yeah. So yeah, because I'm still doing 560 at 5:30 on that Tuesday, but well, yes, some instructors have learned over the years that they've made the mistake of giving a test in the last class before Thanksgiving, and incur considerable wrath from that. So,
my students are having a test that week, but I asked them when they wanted it done, and I have the results recorded in Canvas, so they can't even tell me I did not.
So they opted for this?
Huh?
They opted for this?
They did.
Is it Monday or Tuesday?
Monday.
Oh, okay, that's different.
Yeah,
I had everyone except for one student, and she's like, I'm gonna be out of town. I'm like, honey, that's why I wanted to see who
Yeah,
said
that's
what,
why-
so I can make arrangements for those.
And that's
One or
why I have
two.
my class testing tomorrow is so they don't have to test next week before Thanksgiving.
Okay.
I only have like 11 students, so.
Oh, okay.
I don't like the 2 breaks. I think, like Ole Miss did, just the whole week of Thanksgiving off and no fall break.
Yeah, and I know we were contemplating that at one point. I don't remember what the reasoning was for keeping it the way it was. Because, yeah, I've been at institutions that have the whole week off for Thanksgiving, and it's like, oh yeah, this is great.
I've been at places where you don't even get a fall break, you just get Thanksgiving break.
Oh,
Is it long or just a couple days?
It's the same time as here.
oh, that's mean. That's mean. Okay.
That's Florida for you.
Now I see packing up. Now I'm done, but I want to see if anyone has any homework questions.
You'll be proud, Dr. Lambers. I have all but 2A completed.
Sorry, Chelsea.
I thought we were.
Well, I did kind of create that vibe, I guess, but yeah. 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 All right. Well, unless no one has homework questions, in which case scram anyway, but so.
Hey, I told my students for their test next Monday, I was like, now, if you just happen to leave after the test, I can't force you to stay for the extra lab time.
Yeah, there you go. Well, okay, does anyone have any homework questions?
Samson doesn't.
Well, that's the way to put your finger on the pulse of the class there, I guess. But you appear to be correct.
Yeah.
Okay. Based on what I plan to cover on Thursday, there will certainly be time for homework questions then. Because I've talked to some of you about where you're at, so I know that progress is being made for the most part. So let's make sure that no one's in a bad situation come December 10th or 11th or 12th. But okay, so all right, we were done.
I know yesterday when my class finished early, I was like, okay, we're gonna have open lab time, but if you don't want to stay for that, I can't force you to stay for that. So I was like,